Thank you, Scott. Very happy to be here. My partner over there is getting mic'd up, but I'm just going to go ahead. Yeah, so my name is Muir Manders. I'm on the client side of the source control team at Meta. And today with Rajiv Sharma, who's on the server side of the source control team at Meta, we're going to be talking about marrying Meta SCM with Git and achieving the best of both worlds. So we'll start with an overview of source control at Meta, and then we'll look at the resurgence of Git at Meta in the last few years. We'll look at Git in Mononoke, the server, and we'll look at Git in Sapling, our client. And then finally, we'll take a look into the future. Right, so kind of like a flyover of source control at Meta. We have a very large monorepo, tens of millions of files, tens of millions or more commits, and terabytes of working copy size. In terms of repo growth, this graph is actually from 2017 when former colleague Durham gave a talk here. And this is the current graph. And if I superimpose the old one on the new one, you can see that our growth has accelerated, to say the least. If you're curious as to why it's shot up so much, I believe that's actually when Rajiv joined the company, and he just puts out a lot of code. Good, someone laughed at it. Jokes aside, it's actually from merging separate repos into our monorepo. And yeah, Meta continues to derive a lot of benefit from investment in the monorepo infrastructure. Right, so what pairs well with a huge monorepo? It's a very lazy client that avoids doing work up front. By lazy, I mean when you clone this big repo, you don't fetch any file data or any directory data up front, and you fetch a very compressed commit graph. Here's a screenshot of me cloning our monorepo FE source. It clones in around 3 seconds, and I downloaded around 7 megabytes of data. And it's not like a truncated, history is not truncated. You can see all the history, you can see all the files if you look for it. It's just downloaded on demand. And I'd say the third kind of pillar of source control at Meta is our stack-based workflows. What does that mean exactly? A stack is like a series of commits that depend on each other, like unlanded draft commits. And then the workflow refers to source control adjacent tooling. That makes it really easy to work with stacks, and in particular, incrementally work with stacks. So it's not all or nothing, you kind of go piece by piece. And that's for whether you're authoring commits, whether you're modifying them, submitting them to code review, performing code review, or landing them. Kind of have tooling at each of those steps to make it work well. And here's a screenshot of Sapling's smartlog UI, which you don't really have to understand, but it's just know that it's showing you details about only the commits that are relevant to you, all in kind of one shot. Okay, so let's do a quick tour of the different source control products at Meta, starting with Sapling, which is our CLI program, SL, used to interact with local repos on your system. It's analogous to the Git or HG programs. It's descended from Mercurial. It's, Meta had Mercurial fork for a while, and Sapling is just kind of the rebranding of that fork. The UI has evolved significantly over time, and most of the internals have been rewritten at least once. It features the interactive smartlog GUI, which we'll demo later, kind of a favorite of developers at Meta, and it's officially open sourced at this website. You can find lots of technical documentation and other interesting stuff. The next piece is EdenFS, which is our source control aware virtual file system. And it appears to the user that they've got the entire repo in a directory, if they can, CD in and look at all the files or whatever, but everything is downloaded lazily on demand as the user accesses the file system. It supports Fuse, NFS, projected FS, which just means it works on Linux, Mac, and Windows, multi-platform support. It integrates seamlessly with Sapling, so if a user clones a repo using Sapling, they often might not even know they're using an NFS. It's all kind of transparent to them. And it has local APIs that local tooling, build tools or whatever, can use to access source control data without going through the file system, makes it a bit faster. And its source control is also available on GitHub. And the final piece is Mononoke, our source control server. It's a highly scalable, blob store-backed distributed system, meaning it's not just one server, it's actually multiple servers working in concert. It has some really cool specialized tooling designed to merge repos into the monorepo and make that painless and seamless transition for users. It also integrates seamlessly with Sapling. The arrow between Sapling and Mononoke is actually a custom Sapling remote API protocol that's used to enable a lot of cool features we have. And the source control is also available on GitHub, not fully productionized yet. Okay, let's look at the resurgence of Git at Meta. Starting with brief history of Git at Meta. 2013, we began transitioning from Git to Mercurial. That migration was pretty much complete in 2015. In 2017, Durham gave that talk about Mercurial scalability and user experience wins at GitMerge. So it seems like Git was pretty much done at Meta. Quite the contrary, Git has experienced a resurgence in the recent years. So return of Git, why did it experience a resurgence? Very interesting. The underlying factor, I think, is just Git dominates the industry. So it's inevitable for some influence of Git to trickle into Meta. And that's played out kind of over time as we've seen Git users at Meta grow slowly, whether it's from acquisitions, where the developers preferred to use Git and they kept on using Git inside Meta, or recently AI research tends to be a Git-heavy workflow, often using GitHub to collaborate internally and externally. GitHub and the open source world in general, basically uses Git, and Meta itself has some Git-first projects such as PyTorch, which is source of truth on GitHub. There's the Android open source project, which is a dazzling constellation of thousands of Git repos that you use to build Android, which is important to Meta. So Git is important to us. And at the end of the day, we love monorepo, but it's not practical to put everything in the monorepo. And kind of another angle is that we build a lot of source control tools at Meta. We want to share them with the community. If there's no Git story, like everyone uses Git, so if they don't work with Git, then it's kind of a hard sell to get people to engage with them. All right, so quick poll of the audience. Hate to be that presenter, but how many Git repos do you think Meta hosts right now? 800. It's close. Closer to 10,000 and growing. Rajiv, you should have known that. Okay, I'm going to pass it over to Rajiv to talk a little bit about the server.
Okay. All right, let's see if I can work this thing. Never mind. Okay. All right. Thanks, Muir, for that overview of Meta SCM. One of the components that Muir talked about was Mononoke, the scalable and distributed backend that powers Sapling repos at Meta. But the reason I am here today is because Mononoke also speaks Git. In fact, Mononoke speaks multiple protocols, like Sapling and Git, but for the same repo. And by the same repo, I mean that you could Sapling clone that repo, make changes to it, Sapling push it, and Git clone that repo on the other end with the latest changes. So it's one single repo, but in multiple flavors, which I think is pretty cool. And once it's fully open sourced and productionized, you'll be able to host your Git repos in Mononoke without major changes. Compared to our internal Git servers, which is a basic deployment of vanilla Git, Mononoke has up to twice as faster clones, exponentially faster blame, file log, file history, and all such operations. Exponentially faster is ancestor checks for answering queries like, is commit A an ancestor of commit B? And to top it off, it's horizontally and dynamically scalable. So how does Mononoke achieve all of this? Well, there's a lot that goes into it, but one of the most fundamental factors is derived data. Derived data is Mononoke's framework for generating pre-computed indexes for optimizing operations. These are created per commit, but asynchronously, so that your pushes don't get blocked or slowed down. These are targeted towards solving a specific problem. For example, when we wanted to optimize the blame experience for users at Meta, we created the blame derived data type, which does just that. Derived data is essentially Mononoke's strategy for trading off space for extra performance. And that's quite in contrast to what Git does. And it is through the use of derived data that Mononoke achieves high performance. Now, before we try to understand what Mononoke optimizes, let's have a look at what needs optimization. Let's start with a very basic Git read workflow that you all are probably familiar with. So it starts with the client sending all the refs that it has to the server, in this case, A and B pointing to commits C1 and C2. The server then computing the set of objects needed by the client, and then sending those objects over to the client in the form of a pack file. Now, with this high-level overview of the process, let's try to understand what can slow it down. Clones can get slowed down if finding the commits and objects to send takes a long while. The objects that are included in the pack file are packed at runtime instead of beforehand. And finally, due to laws of physics, if the pack files themselves are large, clones are naturally going to be slower. So let's start from the bottom. Let's look at why pack files are large and what's contained in them. Pack files are made of simple Git objects, but compressed, so to save on space. And they're also made of partial objects, which are expressed as deltas of other objects. So for example, in this case, B2 is expressed as a delta of B1. A very natural question to ask at this point is, if we can use deltas, then why do Git pack files end up becoming larger than necessary? Well, it's because Git can't always make the right choice for objects to be delta. It's important to note that the efficiency of a delta is heavily dependent upon the source and target object. If these two objects are similar, we get an efficient and small delta. But if they're very dissimilar, then that's a delta that we do not want. So why can't Git make the right choice? Well, it's because Git is operating with a very limited information set. All it knows about the object is its size, its name, and its type. And that's just not enough information to make the correct decision all the time. Fortunately, Mononoke does not have this restriction, which is why the pack files that are generated by Mononoke are up to 50% smaller than our internal Git servers. And not just that, it's available for any commit that the client might need. So it's independent of Git GC or Git repack, including that object in the pack file beforehand. And how does Mononoke do this? Well, it's derived data once again. In this case, a particular type of derived data called as Git delta manifest. You can think of Git delta manifest as a pre-computed index that creates and stores deltas of Git objects by diffing them with their parents. So let's say we had a commit C1, like you can see here, with trees T1, T2, and blobs B1, B2, B3. Now its child commit, C2 comes along and modifies B1 to B1 prime, and by extension the T1 to T1 prime. The Git delta manifest for C2 would include B1 prime as a delta of B1 and T1 prime as a delta of T1. Of course, I'm oversimplifying, but you get the idea. So the question is, why does this strategy work? Well, it works because deltas between consecutive versions of any object usually gives the minimum size. And if you think about it, intuitively it makes sense. Because whenever we are modifying our code, we add a function, we remove a method, or we refactor a class. Any particular version of our code is usually a closest match to its previous or the next version, which is why this strategy works. Once you have this Git delta manifest at hand, all the server needs to do at request time is to weave them together into one single pack file that is needed by the client. And the beautiful thing is that it can be done at minimal compute cost. All of this leads to smaller and cheaper pack files that lead to faster clones. Now let's talk about another key aspect of Git, which is its commit graph. Git has always had the notion of an implicit commit graph, but since 2018, it became explicit. Git's commit graph is, the current version at least, isn't quite optimized for large repos. This is because it performs linear scans, and these linear scans can result in slow pulls, either due to multiple back and forths between client and server, or more time spent by the server to decide the set of objects to be sent to the client. And it can result in slower responses to is ancestor queries, which are used in various different Git operations. Mononoke's commit graph avoids these linear scans, which gives it large speedups. So how does it avoid these linear scans? Well, because of its skew binary nature. Now, if you don't get the term skew binary, don't worry. To be honest, I don't get it completely either. It's essentially a commit graph with binary search. So let's say that you had a commit graph like this, with the client having a ref heads main and the server having the ref heads branch. From looking at the visual representation of a graph, you can easily figure out that the common ancestor or the common commit here is the one at the bottom, and the set of commits to be sent from the server to the client are the ones shaded in green. However, with a standard commit graph, to arrive at the conclusion would require touching every single commit. And so it's easy to see why it does linear work in this case. In contrast, Mononoke's commit graph touches far fewer commits to arrive at the same conclusion, performing logarithmic work. An optimized commit graph is key to more efficient clones and pulls. Let's step outside the world of git push and git pull for a moment, because Git is much more than that. Wherever you work, you probably have a UI surface which you use for browsing your code, looking up files at a particular commit, blaming the contents of the file, and so on. All of those workflows are also powered by Git. However, Git by itself isn't quite optimized for these use cases. And if you think about it, it does make sense. Trying to answer these queries by running raw Git commands on the Git server doesn't seem like an ideal strategy. If these queries are expensive or if they're for a large repo, they might end up competing with user traffic for that repo. And finally, because these queries are in the form of Git commands, caching them isn't quite easy. Mononoke solves this problem by creating a dedicated API surface called a source control service for all non-repo checkout-based access. And like pretty much everything else that I've talked about till now, this too is powered by derived data. Every time the source control service gets a request for file history, file log, blame, etc., instead of running git commands, it uses, oh, sorry. Oh, there you go. Instead of running git commands, it uses pre-computed derived data to answer these queries. And this derived data has been generated specifically for this purpose. And it's the use of this derived data that makes a fundamental difference. Let's try to understand that difference through an example. So here I've opened up just a random file in the open source Chromium repo. And right now, I am trying to pull the history, file history for this file. And just to emphasize, this is just a random file. It's quite small, as you can see. And the view that I'm viewing it right now in is the code browser that we use at Meta, called at Code Hub. And as you can see, it took a long while to actually fetch the history, about 23 to 24 seconds. Now, file history for the same file in the same code browser, but with the source control service as a backend. Let's see how that goes. Almost instantaneous. It takes about a second, which is like 20 times faster. In addition to being fast, the API queries of source control service are a natural candidate for caching, so that we don't spend any unnecessary compute on repeatable operations. Source control service provides 10 to 20 times speedup for dozens of such use cases only through the power of derived data. Let's talk scalability. It's not exactly a secret that scaling a Git server with an on-disk repo is challenging. And if you think about it, it makes sense because every time you want to add a server, you have to wait for all the repos to get bootstrapped on the server before you can start serving traffic. It forces you to trade off between durability and push throughput. And finally, it prevents you from hosting very large repos. If your repo is bigger than the disk itself, then you're forced to scale vertically, which is much more expensive. Mononoke, on the other hand, was designed as a distributed system from the get-go, and hence it can optimize for both durability and scalability. It can optimize for durability by keeping the server stateless. So after a push, if one or even multiple servers go down, there is no risk of data loss. It's also incredibly easy to scale because all that's needed to add a new server is for that server to boot up, and then you're good to go. Let's now shift our perspective a bit and look at Git from the client point of view.
Am I on? Oh, there we go. Thanks, Rajiv. Yeah, shifting gears now, let's talk about Git and Sapling, the Meta's source control client. So first, I think it's worth diving into why should Sapling even support Git. So internally at Meta, the difference between Sapling and Git for developers started to become more painful. And what exactly were those pain points? Well, slower clones, other scalability issues. Some of our Git repos grew large in their own right, and things just get slower the bigger they get. Our stack-based workflows are somewhat more difficult using Git. I have a little example here using the Sapling absorb command to exemplify kind of how Sapling helps you deal with stacks. So here I have 2 commits where I added a new library and I added a user of the library that calls into it. And I woke up in a cold sweat last night. I realized I gave things really bad names. So I come in, the next morning and I do a search and replace, and I've replaced bad name with good name, much better name. Right, so now I have changes to 2 files and they touch both commits. So with Sapling, you just run the absorb command and it figures out which change goes to which commit, and it just applies it all right away. These kind of features can be implemented in Git. I think this actually has been implemented as a Git extension, but this is just kind of one example. These stack first commands pervade the Sapling command surface. Right, and there's no Git GUI that's tailored to our workflow like the interactive smartlog GUI is, which I'll demo later. And Git is not commit cloud capable, and commit cloud is a feature with our internal repos where you make a local commit, it's automatically uploaded to the cloud, and then you can share just the commit hash with a coworker to collaborate, or you can use that to like submit CI job or whatever. It's just lowers the friction. And another reason I mentioned before, Git dominates the industry. We wanted to get Sapling out there, but no one probably would use it if it didn't support Git. Okay, so what does Git support in Sapling look like? In 2022, we open source Sapling with new support for Git. Here's a screenshot of me cloning a repo using Sapling. So I use the SL command and I clone a GitHub URL, and it fetches it and checks out master. If I run just SL, this defaults to the smartlog command, which in this case shows us 1 commit, which is the commit we currently have checked out, and that's the only relevant commit, so it only shows the 1 commit. And then I check out some other branch, my style update branch, and you can notice that it's pulling that branch on demand, because when I cloned it initially, it didn't fetch all branches. It only fetched the one I was going to check out, so it kind of defers work in that way. And then on my branch, I run smartlog again, and now I can see our branch has got a couple commits, and the smartlog also shows the branch base, which is master. Okay, so in this mode, you're using Sapling's working copy implementation, using Sapling's commit graph, and other Sapling components. So it's not, it's Sapling repo at its core. I also want to kind of give a shout out to a new experimental mode that we've added recently, which allows you to use Sapling in an existing Git repo, so you don't have to reclone. It's slightly different trade-offs, but it's really convenient to try out Sapling. Something else that's important to emphasize, you don't get all of Sapling's features when you're using Git protocol, because the Git protocol just doesn't support everything we would need, like especially for all the laziness and things like that. So all the features I'm going to list, you don't get all of them if you just clone a GitHub repo using Sapling right now. Right, and emphasize again that it's not just a UI on top of Git. It's like a Sapling repo that just uses Git at the end of the line to get the blob and the tree data. Okay, so if it's not just a UI, then what else do you get? UI is obviously important, but due to the accelerating repo growth, we spend most of our time on scalability. So Sapling has highly performant commit graph, and when you clone, you don't need to choose between shallow or not shallow. Kind of always starts off as shallow and then gets filled in as needed. It only uses order the number of merge commits space on clone, the commit graph. Can do a greatest common ancestor calculation in log n instead of having to scan. Sapling has the material rev sets still, and it has very fast rev set calculations. Common operations like log, bisect, copy tracing also don't perform linear scan, so they're a lot faster. And another key feature is even NFS support for lazy working copy. So if you have a large working copy and you have to write all those files out, things are going to be slow no matter what. So to make things snappy, you defer writing files to the working copy until they're accessed, which gives a much more pleasant user experience. And Sapling's local repo storage doesn't require explicit repack or GC operations to maintain performance. And finally, certain operations like adding a file are still performant on very large working copies due to incremental updates of the working copy state. A lot of these topics have detailed documentation on the website if you want to kind of read more about them. Okay, demo. Good thing I put that slide, I would have forgot. Okay. So now I'm going to demo the interactive smartlog GUI that comes with Sapling. Currently, I'm using it in the browser. It also runs as like a standalone app and as a VS Code extension. And I also want to take this opportunity to address kind of a common comment people make that Sapling doesn't have a staging area, which people kind of like a lot. But similar to JJ, we kind of have a different approach to solving this need, and I hope you see some of that here today in this demo. Okay, so 3 days ago, apparently, I had a inspiration for a new project, and I cranked out these commits to get things going, but I was kind of messy and doing too much in one commit. I want to reorganize. I want to do another pass to clean up this stack of commits. So I can pop into our stack editing UI, and I want to use our split mode, and then I want to choose all my commits. All right, so now in this view where I see my commits kind of horizontally, here's my first commit. Very important program here. And then my second commit, I've added support for printing out the username, key feature. But as you can see here, I fixed a typo in the first commit. Really, that change should be applied to the first commit. So we can just do that here by clicking these little arrows. Click, click. Now if we scroll over, we can see the first commit has the typo fixed. So in our second commit here, we print out the user, but we're ignoring the error. It's not, you shouldn't ignore errors. And in our next commit, we realize that and we added proper error handling. But really, we should have done that from the get-go. So let's click this arrow here and integrate those changes with the previous commit. So now it's all together. One other thing we did, we added some amazing documentation here. Probably too much to do in one commit, so let's just separate the documentation into a separate commit. And I was reusing that, so let me give this a new name there. So we got our documentation here, and then we've got another commit adding a to-do. Okay, things look pretty good now. Save these changes, and there, we've applied our changes to our stack. And one more thing, I like to put my to-dos earlier in my stacks for some reason for the purpose of this demo. So we're going to take this to-do commit, and we're going to drag it down here. And as I drag it, you can see it's also grabbed the docs commit because it knows they depend on each other, and it doesn't want me to cause conflict, so it's dragging the dependent commit with the commit. So let's drag these down one, reorder things, and there we go. We've cleaned up our stack. Yeah, so that's interactive smartlog. And one final time, I'm going to pass back to Rajiv to talk about the future.
Yeah, I know I'm the last thing standing between you and after party, so I'll try to make this quick. Everything that we have talked about and showed you today is the current state of Git at Meta. So a very natural next question is, what comes next? Or are we done? And the answer is absolutely not. We are very excited about the future of Git, both at Meta and in the wider community. We believe that a lot of improvements that have been made so far can also be contributed to upstream Git. Features like an optimized commit graph that does logarithmic work instead of linear, pre-computed indexes that aid in pack file creation, leading to more efficient and smaller pack files. These can also be push-specific improvements achieved perhaps through push protocol v2 for features like auto push rebase, where a user's push is never rejected due to unrelated conflicts. Commit cloud, where a user's local commit becomes CI testable and shareable across the entire organization. And finally, resumable pushes, which splits the pushes into an upload and update phase. The story of Git at Meta has been an interesting one. We have come a long way from mostly ignoring Git to making Git a first-class citizen of our source control systems. Today, Git users at Meta can either use Sapling with a standard Git server, or they can use a standard Git client with Mononoke server, and either way get a better experience. However, we want to go a step further. Our final goal is to add Git support to Sapling protocol that unlocks features like full laziness, where we don't download any unnecessary blobs, trees, or commits, unlocking the full potential of derived data that Mononoke can offer, commit cloud, and auto push rebase. In short, you can see that with adding Git support to Sapling protocol, we'll be able to unlock the best of both worlds. Thank you.